So we'll do rotation. Chapter 12. I'll just go ahead and say part 1. I'm not entirely sure how much we'll get through today, but let's look at what you guys should already know. Okay. Things you ought to already know. If we have an axes like this, X and Y, oftentimes you will see a three-dimensional coordinate system drawn kind of like this. Okay. So yeah, if you're looking at your right-hand rule, you're doing the hand thing, right? Your thumb. Well, start with the L, right? Start with the L. Your thumb is your X, and then your front finger is your Y. Then you just stick this up. This one. Yeah, subtly, maybe not aggressively, and that's the Z. Okay, in the middle finger. I don't. If you, can you do? You can do Teenage Mutant Ninja Turtle style, like 3 fingers. That'll work. Okay, so I'm pretty sure you'll get in trouble if you write on your hands like XYZ. Don't do that on the AP exam. Just make sure you know. Make sure you do not ever use your left hand. You must use your right hand, or else your directions will be wrong. Okay, if this is your coordinate system, let's say you have a disk. So I'm going to try and make it a little 3D. Okay, so let's say it has a little thickness. Okay, so by our convention, if it rotates this way, counterclockwise, is positive omega. Oh, right. I grabbed that. Oh. Positive omega in the Z. Okay. That is the direction of the omega vector. So you could say omega, the vector omega equals to omega Z in the K unit vector direction. Okay, in case you forget, if X, Y, and Z is like this, then your unit vectors would be I, J, and K. Okay. Questions on any of this stuff? It's been a little while since we've done unit or vector notation, so you can go back over it. So then a clockwise rotation is negative. Right. So some terms that you should know, just reviewing a little bit, we have theta is angular displacement. Or sorry, angular position. Displacement would be the difference. Okay, angular position. You have angular velocity. You should really try and distinguish omega from a W. Yep. I think when you Well, think of a position vector in terms of just normal position vector, like r, right? How is that a vector? Usually it's in reference to some sort of origin, right? Some in a reference frame. So like you have how much in the x direction relative to 0, how much in the y direction relative to 0, so on and so forth. So in the same way, an angular position is some degree measure relative to some 0. Usually the x-axis is 0 degrees, but it's pretty arbitrary. It's true. You have to have some predetermination for a certain reference frame where 0 is, and usually x is going to line up with the 0. So then when you measure from there, counterclockwise is positive, and so on. Okay, and then lastly we have alpha, which is an angular acceleration. Make sure you do all of these in radians. Sometimes you'll be asked to convert to degrees, or you'll be asked to convert to revolutions, things like that. So make sure you're familiar with these units: radians, degrees, revolutions. Okay. And again, that's not just the regular A. You really need to make sure you distinguish alpha with these long curly long tails from just A. Especially in a free response problem, if you just write normal normal A instead of Greek alpha, you might not get points for that. Okay. We also had talked about this normal A with a T sub T. This is tangential acceleration. Okay, make sure you recognize what they represent or mean. We also talked about tangential velocity. And then we also had S, which is like an arc length. If you want to keep with the verbiage, you could say a tangential displacement, or yeah, I guess it can still work to talk about a tangential position. That's a little weird, so I'm gonna put that in parentheses. Usually you'll see it more like an arc length. Yeah. And then we also had a centripetal or radial acceleration. And I'll put in parentheses centripetal. Let's see. Yeah, I mean, as far as whether it's positive or negative, usually positive is going to be inward. Okay, if it's being pulled in, it will go in a circle. So usually that's the case, but maybe safer to just say inward. Just inwards, right the direction. Okay, we also had tau, which is for torque. Okay. Now I'm going to add a couple other ones. We're going to have I. It's called the moment of inertia. Sometimes it is called rotational inertia. this is a new one. I'll put a star on it. That's new. Okay, and then we're going to have a rotational kinetic energy. That's also going to be new. Okay, so again, be very familiar. It's going to be super important when it comes to rotation, which students always get mixed up, is they look at all of these different letters, these variables, and they're unable to visualize or understand what they represent. You need to understand what they represent. Or else, if you start confusing this A with this A with this A, you're going to get super confused. Okay. Make sure, honestly, for me, when it comes to what makes physics, how I sort all these out, make flashcards, and it's not even a word definition. A verbal definition of these is not really going to help you that much. Try and draw a picture or a diagram for these to visualize what they represent. Your tangential velocity is like if you have a speck of dust or an ant sitting at the edge, how fast is it going in terms of translation, like in terms of its directional movement, displacement. Whereas angular velocity is like how many degrees is it changing, is it sweeping through each second, right? So sort through that stuff, that's important. All right, so now what we'll do is we'll organize this. I really like trying to draw the parallels between linear and rotation. And we've done this a few times, but if you can sort all your rotational terms in parallel to all your linear terms, it makes it a lot easier to, you end up kind of memorizing less because you can just draw the parallels between. So R is like theta, right? V, which is the change in R, time, is like omega, which is the change in angle over time. A is the change in velocity over time. So alpha is the change in omega over time. Your tangential velocity, or sorry, your tangential acceleration is related to your angular acceleration by that. Your tangential velocity is related to your angular velocity by that. And this arc length S is related to theta. And let me just go. So yeah, some of these equations are not on your equation sheet. If you look at what the equation sheet has, oh, sorry. When it comes to this, if you can just kind of memorize in general your linear tangential part is related by R, pretty much multiplying the angular one by R. If I look at this, there's this one, and then that's it. I don't think they have like S equals theta R. They don't have tangential acceleration equals to alpha R. They don't have it on your equation sheet. But this one is kind of just replace the V's with A's and alphas or thetas and S's, right? And then you get the same thing. All right. Yeah, they don't have any of these other definitions either, but that's really a definition, so you should know that. Note that these really only work for circular motion. Because implicit in this is that at this particular moment, your velocity or the direction you're moving is perpendicular to your radius. If it is not, which when we get to gravitation next unit, when you get to orbits, orbits are elliptical. They're not perfect circles, which means sometimes you're coming a little bit in, sometimes you're cutting a little bit out, which means you're not moving perfectly perpendicular to your radius, and then you can't use this stuff. It doesn't work. Yeah. Angela's. Okay, what else do we have? Going down the list, we have these. We have the radial acceleration. That is this one. Okay. And with substitution, you can get this. But remember, the units get a little wonky when you use this one. Careful units. Because you end up with like radians. This is supposed to be a meters per square second. And the way the radians kind of are a non-dimensional unit can be a little weird. Okay, and then we have torque. So none of this circular motion stuff has a linear parallel. But when we talk about torque and Newton's second law, okay, this is where the sum of your forces is equal to ma. So this is kind of new. So your sum of your torques, you're gonna need some sort of mass, like a rotational mass, times some sort of rotational acceleration. I'm gonna write this first. We said torque is kind of like a force, R cross F. Okay, so you're summing all the torques created by your forces, and that will equal to I alpha. So I is like a mass, a rotational mass. If mass is inertia, is a measure of inertia. So inertia meaning it's its resistance to its change in motion, right? The more inertia it has, the more mass it has, the more force it takes to change its current state of motion, to accelerate it, right? So it's the same idea. The more rotational inertia it has, the harder it is to get something to start spinning or to stop spinning. And then that's alpha. So we can say that mass is like an inertia. Or sorry, is like a moment of inertia. Okay. For all objects, so with mass does not have any physical, like spatial dimension to it. It's just how much, usually it's related to how much matter is in an object. Your moment of inertia is entirely dependent on the mass of the object and the shape. Okay, so what ends up happening is you can calculate this moment of inertia, this value, with some sort of CMR squared. This is for any sort of, how do you describe it? Rotationally symmetric objects. Okay, so rotationally symmetric objects, that's like spheres, cylinders, rings, discs, or if you have like a rod that you're spinning about a certain axis, right? You can do that too. We'll come back to this. In general, more generally, you get something like this. In other words, it is the sum of all your masses times their distances from some sort of pivot squared. We'll look at this one in a minute. Yeah, this will take a little practice. Okay. The last thing to bring up, actually, let's do rotation. So usually with kinetic energy, we have like a 1/2 mv squared. So for rotational kinetic energy, if you had to guess, what would it be? Perfect. Oops. 1/2 I omega squared. That's it. So the hardest part about rotation is not going to be this. It's not going to be k. It's not going to be tau. What usually makes it difficult is I. I is the hard one because you have all these different moments of inertia for different shapes. And so we'll take a look. Okay, there's one last one, and I kind of ran out of space. If you still have space, you can throw it in. It is, how do you calculate a center of mass? And that is sum mass of a particular component, a piece of your object, divided by the total mass. I guess actually I should say this is R in the X, and this one is going to be the sum of them and the Y. Okay, so if these are like, what is it talking about? That's what we're going to do next. By just throwing it out there so we can use them. Okay, so this is new. This is new. That's new. That's new. This is new. The other ones you should know. So these ones I have peppered into what we've done so far so that when we got to this unit, you didn't have to do all of this and all of this. Yep.
Is the capital M mass?
It is like the total mass. This is like total. So let me give you an example of calculating center of mass. Okay. What does that look like just off the bat? Does anyone kind of have an idea of what that kind of represents? When you take the sum of positions with like a factor or a coefficient, and you divide by the total, it's kind of like a weighted average, right? You think about it in that sense. If you're looking at the positions of a bunch of objects weighted by how massive those objects are, and you divide by the mass of the entire system, that ends up giving you kind of a weighted or a preferenced position, right? So, all right, let's take a look. You good? Yeah.
What's the difference between the sum of the small m's and the big M?
So the big M is the total mass, and so what you're doing is you'll see. When we get to the example, it'll make a lot more sense. Okay, so again, I'm skipping the derivation here so that we can just jump to an example, and then I think that'll make it make more sense. So let's look at center of mass. So what center of mass is if you are in deep space. Let's say you're in deep space. At least this is the way the book introduces it. I'll add a little more to it. If you're in deep space and you take something and you just start to spin it, there is some point on the object that, as you spin it, is stationary. There is a position or a spot where it will favor spinning around. That's the center of mass. Okay, it's where all the other objects want to rotate around. Let's just go with that. Okay, we'll save the deeper meaning behind it later. So, okay, let's do this example. Let's say you have a 2 kilogram ball attached to a massless rod. Massless. And then you have a 500 gram ball on the other side. 0.5 kilograms. Right? So the question is, if I take this baton and I throw it in the air, where is it going to want to spin around? Qualitatively, you'll probably say it'll spin more around this, right? Because this is the more massive part. It is harder to speed up, slow down. This is easier to speed up, slow down. So in a certain degree, you know, they both have to have the same angular acceleration. You can't have one object have more angular acceleration than the other, or else that means it's like bending, right? So at a deeper level, it's kind of talking about how the system has to rotate at the same angular acceleration, which means that it would have to balance out each tangential velocities and so on and so forth to balance all the inertias. But, okay, so where's the center of mass? So if we choose my coordinate system to start from here, okay, x and y. When you're doing center of mass, choosing where your coordinate system is a big part of it. Same thing with when we get to moment of inertia. Pick a convenient spot, something where you know information about. So if this is 50 centimeters or 0.5 meters in length, okay, so the center of mass in this x direction is going to be, I'll write this out again, M-I-R-I-X divided by total. Okay, so let's look at our pieces. We have 2 kilograms at 0 meters plus half a kilogram at 0.5 meters, all divided by 2.5 kilograms. It's essentially a weighted average. You're going to get, 0.25 divided by 2.5, or it's about 0.1 centimeters. Or sorry, meters. Okay, so 0.1 meters from our origin, which is like right here. Which should kind of make sense because 2 kilograms is 4/5 of the total weight of the total mass. 0.5 kilograms is 1/5 of the total mass. So you can kind of see that the center of mass is 4/5 over to the left. If that kind of makes sense, how it's kind of weighting that positioning. Okay. How's that? So that kind of makes sense how I'm using the calculations. We can try another one too. Yep.
If you did it the opposite way around, would it work too? You set the origin on
this side?
bottom, right?
Yeah, we can do that too. So let's say, I think that's a good exercise. We'll do the same thing. What you'll find is really it doesn't matter where you put it, but you want to put it somewhere where it's convenient to do the math. So like if you put it at like 0.35 centimeters from the left, like then you're going to have to do some extra calculations there. It's not necessary. But we can do it this way too. So if here, you can point this way, x. Okay. So same thing, center of mass equals to, in this case, now you're going to have 2 kilograms times 0.5 meters plus 0.5 kilograms times 0 meters divided by 2.5 kilograms. In this case, I put x pointing to the left, so it wouldn't. However you point your x, though, you do want to be very consistent with, is it in the direction of x or in the opposite direction of x? So yeah, you're right. If I point it in the right to the right, then it would be a negative x, which means I have a negative x. See, I'm sorry. Yeah, be absolutely sure you be consistent, because we will run into problems where our origin will have objects to the left and to the right and above and so on and so forth. Okay, so then this will end up being, or let's see. Yeah, 1 kilogram. Is that right? Yeah, 1 kilogram, or sorry, 1. Was this what? 0.4 meters. Yeah, that's right. 0.4 meters this way. But again, now your origin's over here, so now you're measuring 0.4 meters out. Right? So it's the same spot. It's just that your origin's in a different spot. So. Okay, let's try another one. Here, we'll just do it like this. Example 2. Okay, I'm going to use this grid. Okay, so let's say this is actually marked off, right? This will be 1, 2, 3, 4. Same thing, 1, 2, 3, or negative, and 1, 2, 3. All right, let's say we have an object here, and an object here, and an object here. Okay, so this is at 3, 3, negative 3, 3, 0, negative 3. Okay, let's say this is the mass of 1 is 3 kilograms. The mass of 2 is 5 kilograms. And the mass of 3 is 8 kilograms. Oops. Okay. So, how do we do all our center of mass stuff? Well, we're just going to sum it. Yeah. We're just going to sum. Okay, so we'll start with the first one. In terms of the x position, it is 3 kilograms times a negative 3. We'll just keep it unitless. It's fine. It doesn't really matter. As long as they all have the same units, your final answer will be in whatever the units. This could be miles, feet, inches, meters. It's all the same thing. And then I'm going to add this one, plus 5 kilograms times 3.
Wouldn't it be 3 root 2 because you're finding the distance
X
from the origin?
is just x. Sorry. If you go back to the way I wrote the sum, it is just the x component. So you don't actually have to find the full distance, because you're not trying to find you have to break it down into its components if you're trying to find center of mass. So right now we're just trying to find the x location of the center of mass. So we're just doing the x coordinates. And you'll see I left out this one because it's 0. in the x direction. And then the total mass is 16. So this ends up being, let's see, 15 minus 9, 6 over 16, or 3/8. So about 3/8. So it'd be like somewhere around here. Right? Now we have to figure out the vertical center of mass. So we'll do similar thing. The first one, 3 kilograms times 3. Now it's a positive 3 because we're looking at the up and down. Plus 5 kilograms times 3 again. Looking at the up and down. And then plus 8 kilograms times negative 3. All divided by 16. So we'll get 0. Okay, so the center of mass is going to be like right here. Sometimes we indicate center of mass with the symbol, a circle with a cross. So what this means is that if I could connect these 3 objects with like massless rigid rods, and I threw it and I made it spin, it's going to spin about this spot. Okay, it doesn't always spin about the geometric center. It spins around a weighted mass center, right? Center of mass. Yeah.
So the units you would answer this in are just
The distance units, whatever the distance units are. So if everything was measured in meters, you do it in meters. If this is unitless, then it's unitless. But if I made this like 3 meters, then this would be 3/8 meters to the right of this spot, and so on and so forth. These are all length measurements because the mass divides out. The mass divides out. Okay. So I'll take that as an example actually, because I noticed that Jeremy was spinning his pen, right? You want a nice balanced pen if you're spinning a pen, which I can't. I'm not very good at. But if you ever try and spin a pen where it's like really heavy on one end and the other, you can't do it. It's really hard. Kind of the same idea. Is that when you spin it, you want it to spin where it's resting on your hand. Right? Okay. Yep, Ben. Oh yeah. That's a very good example too. Do I have a hammer? No, it doesn't work with liquids. Liquids are really tricky because it's all sloshing around. A lot of what we're doing in chapter 12 is pretty specifically for a rigid body. Okay, that is an important thing to know. It has to be a rigid body out here.
So if there's no air in the game compressor, it doesn't matter.
Whatever, it's spinning like closer to here than anything else, right? Spin this way. Right? It's spinning a lot closer to where it's heavy or where the weight is concentrated. So it's actually also kind of interesting. This is all 2 dimensions. Okay, everything we're doing for this unit, for the most part, is going to be 2 dimensions. If you start making it 3 dimensions, it gets very, very complicated. For example, if you take your phone, you flip your phone, you'll always notice that it will never spin like this. It will always twist. No matter how hard you try and throw it so that it just goes like this, it will always twist. Because the weight isn't balanced in such a way, you got the battery, you got all sorts of stuff in there, where it spins around its principal axes. Principal axes means that it's not just this way and it's not just up and down. So it won't just spin like this either. it's at an angle. So it's going to try and conserve that angular momentum in such a way where if you spin it like this, what you actually need to do is spin it in a different axis to make it spin only in that axis. Trying to find that axis is kind of tricky, but that is the idea. Questions on center of mass? How to calculate it? Would you like to see another example? One more example? Let's do this. Okay. This is... Sorry. Let me go back. This is the easy version. This is if you have discrete particles, distinct objects that have a concentrated mass. What we did here is we treated these spheres as if they were uniformly weighted so that you can kind of treat them like all the weight is concentrated in the center. But what if you don't have a spherically symmetric object? Okay, what if you have like a rod that has weight distributed all the way through it? Oops. Then you're going to have to modify how you count where all the weight is. Okay? Especially if you're looking at, well, yeah, we'll go with that. So, what that means is when you calculate this, you need to chop up your object into a bunch of little slices of mass, of infinitesimally small masses, and then add them up. So what you end up with is an integral of x dm. Sorry, all 1 over big M. And in the y direction, you can get 1 over big M integral y dm. Okay. A couple comments about this that can make it very tricky. First, let's interpret what this is saying in terms of the mass. You're taking an object, you're not chopping it up into infinitesimally small slices of space, you're chopping it up into infinitesimally small slices of mass. Oops, that should be a little m. Okay, there's a really important distinction with that because what an infinitesimally small slice of mass is does not tell you how thick it is. So here you're integrating with respect to space, but you're looking at a slice of mass which is like not a spatial measurement, right? It's like trying to integrate or add up a bunch of space with respect to time, or with respect to something that's not space, okay? And that can get really tricky. So how do we go about doing that? What you always will need to do, okay, and this is going to come up, and I know you guys haven't done integration yet, right? I mean, in Calc AB.
Nope.
You haven't started it. Okay. That's fine. This trick is not so much an integration thing, but really more just a math thing. Okay, so think of it more like this. Let's say whenever we're dealing with calculus, if you look at infinitesimally small stuff and it's super confusing, don't use such small slices. Use a certain amount of mass, some delta m. You'll see that deltas always end up kind of becoming the differential amounts, because you just take a delta amount and then you squish it down until it's really small, right? You just the difference is just taking the limit as it goes to 0. So if you have a really small amount of mass, not infinitesimally small, but you just have some chunk, right? How thick is that going to be? Well, it depends on the density of your object. Okay, it depends on your density of your object. Oftentimes, lambda, this is pronounced lambda, is the linear mass density. Linear mass density. Okay. So what does that mean? That means that how many kilograms do you have per meter of space? Right? Think of it like either mass, linear density, or surface density, or volume density. Volume density just being your typical density. You know, the density of air is like 1.2 kilograms per cubic meter on the surface of the Earth. That kind of thing, right? Density. So if I want to know how thick that is, how can I relate delta x to delta m if I know lambda? Just think about the units. How can I get delta x if I know delta m and lambda? Just multiply, right? I think actually, yeah. So if I want delta x, it'd be like delta m divided by lambda. Or you can say lambda is delta m over delta x. The same idea, right? This is assuming uniform mass density. Uniform means it's the same all the way through. If I'll describe some of the problems that I've had, like some of the structural analysis classes that I took in college. Okay, how can you make this harder? Well, maybe it gets thicker as you go. So it gets more dense as you go from left to right. So then suddenly your lambda is a function of x. And then you can't really do this anymore because this is changing depending on where you are. You can have different shapes, cross-sectional shapes. You can have I-beams, you can have S-beams, you can have U-beams, you can have Z-beams. You have all these, or not S-beams, Z-beams. You can have all these different kinds of shapes for the cross-section. In other words, if you were looking from this side, what does it look like? And then that changes a bunch of stuff too. So for now, the problems you'll probably get, I haven't quite seen one where they throw in some function of linear density in here. It'll probably be a uniform. It'll be uniform. So it's uniform, then you can say something like this. And so how does that translate to a differential amount? That means that dx is equal to 1 over lambda dm. Or dm equals to lambda dx. You can say that. You can only say this if lambda is constant. If it's not constant, then you have to do some other trickery. Okay, so what does that mean? That means that we can take these and turn them into, I'm going to substitute. I'm going to substitute my dm for the dm's. So you'll have like a lambda over m x dx. If you're talking about y, if you have both an x and a y, then you kind of have to break it down into its density in those directions. So you could talk about a lambda in the x, and you can talk about a lambda in the y. And actually, we can go ahead and just solve this straight out. This gives xcm equals to 1/2 lambda x over m squared. Y Oh, just kidding. Let's not do that. Let's not do that. You have to be careful because you have to look at what your limits of integration are actually, and it depends on where you're considering your axis, your origin. So I'm actually gonna leave it right here. You can't really take it any further from here, unless you look at the problem, a particular problem. Let me explain why that is. First, you have to decide where is your origin going to be. Is it here? Is it here? Is it here? Because that's going to determine what x is measured from. If you look at where x is measured from, then that's going to determine what your limits of integration are, which means that are you adding up from 0 to 5 meters? Are you adding up from 0 to 3 meters? So on and so forth, right? You got to decide. Let's come back to this because I think maybe this is a little over. I don't know. Calc AB people, is this like? Are you understanding what's going on? No. Okay. Yeah. Okay. So, how about as far as just understanding the meaning? Let's ignore this last step. Do you understand the meaning behind this and this? Okay, as long as you understand this part, we can come back. We can come back. That's not so bad. This is just doing what we did up here, but what if you had like 5 million different little objects, right? You don't want to do a summation of 5 million objects. What you want to do is try and do a summation of a function of the positions of those objects. So that if you have a function of the positions of the objects, then you use the calculus to do it for you. Okay, let's go on to well, any questions about conceptually what center of mass is, or at least how to calculate it if you have a couple discrete objects? I think when you have distinct discrete objects, it's fine. You just have to make sure that if you're going to do it this way, you have to make sure these objects are uniform. Usually they have to be like uniform spheres or like point masses. In other words, they can't really have their own weird centers of mass that are like at some odd location. Actually, I think if you know where the centers of mass of each of the objects are, then you can use that. As long as you know where the centers of mass are for those objects, then you can use those centers and then you average those, or you do the weighted average of those, and then you can get the total. Okay, let's look at the other thing that is new, that is difficult to calculate or tricky, is the moment of inertia I. Okay, so looking at the equations, look at how similar they are. If center of mass is like this, and your moment of inertia is like this, okay, the difference is this isn't like a weighted average. This is just adding everything up. You're not averaging anything out because you're not dividing by a total. This is just an actual total value. Okay, so I equals to the sum MI RI squared. The other thing to note about this is, in this case, R is not a directional value. This really is the distance from the pivot. Okay, it is the distance from the pivot. Okay, so how do we do that? Well, let's look at this one again. Two kilograms, 0.5 kilograms, 0.5 meters. We said that if we throw this thing in the air, it will start to spin around this point that is 0.1 meters from the left. Okay, this is the center of mass. That's where it's going to pivot. It's gonna spin. So what moment of inertia is a measure of is if I take this and I make it spin, how hard do I have to push? How much torque do I have to apply on it to make it spin faster, to make it accelerate or slow down? That is what this measures. Okay, so if we measure the moment of inertia of this system, you would have 2 kilograms times its distance from the pivot, which is 0.1 meters squared, plus this mass times its distance from the pivot, which is 0.4 meters squared. And you get something like 0.02 plus 0.09. Oh, and then the units of this is kilogram meters squared. So this is 0.11 kilograms meters squared. The units may seem kind of weird, but it's like a rotational, it's like an inertia. Think of this as just like a rotational mass.
And that's the force that you need to push.
It's not the force. So what that means is that if we look at the amount of torque it takes to accelerate it, right? You would need 0.11 Newton meters of torque to accelerate this 1 radian per square second.
I think it should be 0.1.
Is it 0.1?
Yeah, it should be a 0.1.
Did I mess that up?
Yeah, just a calculate.
It was 0.0.
Oh, 0.08. Okay. So yeah, let's look at how that works out. So 1 Newton meter will accelerate this 0. Sorry, I should take that back. 0.1 Newton meters will accelerate this 0.1 kilograms meter squared of rotational inertia 1 radian per square second. Okay. So let's compare that to like if you just have normal force, right? Not normal force, but your translational force. If you have 0.1 newtons, could accelerate 1 kilogram. This thing is. Oh, it's disconnected. Oh, sorry. No, that's not it. Yeah. Sorry.
Save.
I can't. Oh. Yeah, it's charging. Yeah, we're good. Okay. So 0.1 newtons would accelerate 0.1 kilograms 1 meter per square second. In the same way, 0.1 newton meters of torque will accelerate this 0.1 kilogram meter squared of moment of inertia 1 radian per square second. So that is kind of the analogy that you want to apply here. It's like how hard it is to push or pull something is mass. How hard it is to turn and rotate something is moment of inertia. So a couple of things to note. Because it is mr squared, your moment of inertia goes up with the square of the distance things go away from the pivot point, which means that it becomes harder to twist something much faster if you spread it out than if you just make it more massive. So the shape of an object actually influences the moment of inertia a lot more than just how much mass there is. Yeah. Okay, so we'll come back to calculating more complex ones of this, but I want to kind of show you what they have in the book. Okay, so in the book, they have a list of these pre-calculated shapes. Conceptually, okay, I want to just approach this conceptually. Take a look at the values that you see for the moments of inertia based on where the pivot is. Take a look at which ones are the smallest values and which ones are the biggest values. What do you notice makes it have more moment of inertia? Or which one has the most moment of inertia? Which one? The hoop, right? Just straight up mr squared. Which is actually really interesting because if I took all of that mass and I put it all in one particle at the edge and I just swung it around, that would also have a moment of inertia of mr squared. So what it means is that it doesn't actually matter that the mass is distributed in this ring or this hoop. The point is all of that mass is a distance r from the center. So this behaves rotationally the exact same as if I had an axis and I just had like a ball of mass m. Whoops. Just like swinging around. Yeah, like a sling. It's exactly the same. At least in terms of the moment of inertia of spinning that sling is the same as spinning this hoop. Okay, so the further the mass is pushed out or concentrated towards the outside, the higher this is. So if you have a solid sphere, notice that it is less than a spherical shell, because the spherical shell concentrates the mass on the outside as opposed to having it distributed all the way through. This is 2/5, this is 2/3. So this coefficient here is what I had labeled as a C. Where did I put it? This C. The C is kind of like a coefficient or constant that tends to come out when you're dealing with moments of inertia for shapes, for different shapes, right? Same thing here. The difference between spinning it around the center and spinning it around the end, you get 4 times as much moment of inertia, right? And then same thing, compare this, a plate versus spinning it at the end of the plate. Again, you get about 4 times as much. Notice that the B term doesn't matter here. The thickness or the thickness of it, the width of it doesn't matter because it's not spinning around B, it's spinning around A, right? So this is not influencing the distances from the pivot point. So it's all about how far is it from the pivot point. So if moment of inertia, right, influences how much torque or how quickly something accelerates, right? If I apply the same amount of torque on an object, the less moment of inertia I have, the faster it should spin. So I have 2 objects of the same mass. It's the same mass. this one is a hoop, this one is a disc. Or is that the wording they used? It's a cylinder or disc. This is a hoop. So I'm gonna roll them down the table. Which one do you think will get to the bottom of the table first?
The hoop.
This one? Who says this one? This one.
It's the hoop.
The hoop? Why is that?
More moment of inertia.
More moment of inertia.
Oh wait, no. That means it would spin slow. Wait.
Right. Yes, it takes less torque to get this going. It takes more torque to get this going. So if they have the same mass and they have the same torque, gravity. Yeah.
Oh,
This is the whole point of the demonstration. So, I need. Let's go back.
they're both the same mass. Okay, so it'd be the bottom one. Because you have the full, the thick one. Yeah. There's more mass closer to the center of rotation. Oh, okay.
It's quite a big difference, right?
Mhm.
Quite a big difference. Now, actually, it'll turn out that the mass doesn't even actually matter. Which one has more moment of inertia coefficient? The disk, or the disk, right? The disk is 1/2. If this is a solid sphere, it's 2/5. That's 2/5. Yeah, this is 2/5. So 2/5 versus 1/2. So this is slightly smaller, right? So that means that you would think. Now we didn't really talk about the torque, right, and how it works out. But it's kind of like one of those things. Remember when we did a crate sliding down a ramp? That because friction depended on mass and gravity depended on mass, it actually didn't depend on the mass at all. It canceled out. It divided out. It's kind of the same thing. This one is a little harder because you're not seeing sides. That's a little harder. It's pretty. Let me see if I can have a. Alright, let me use these two. Well, yeah, let's use these two. Right? Because it's the same idea. The mass shouldn't influence its ability. Let's choose something where they're more distinct. This is mr squared, this is 2/5. Or, I guess it should be already pretty obvious if this was very similar to the other one. Right? Let me see if I can have something. I think maybe if you're thinking, well, this is more massive, then of course this is slower. Let me see if I can find something super light.
It's the distance away from the center. Yeah.
It's the
positioning of the mass.
well, I mean, let me see if I can find out.
Wait, the mass is like part of the equation. Yeah. But the mass is constant. But the mass is constant throughout. The mass is constant throughout. So what it is that the mass is the same in cylindrical hoop, but the cylindrical hoop, all the mass is compressed farther away from the center. And so it takes more torque to move more Stop. Jeremy. Mass increases in the eye also. Wait, see, R is the big deal because in the center of the loop, all the mass is positioned at the very big distance.
But like, what's the mass?
The mass is constant.
Then why is it even in this? Are we
No, it's
comparing,
constant. It's constant throughout these. This is assuming that the mass is the same for all of them.
So the mass is what?
But if the mass, if one mass is greater, it will affect it, but not as much as the greater.
Ping pong ball and a ping pong ball.
Ooh.
So we're looking at
Where'd he go?
no, you'd be surprised.
Toasted bread.
Well, I consider myself silent. Oh, look at you.
No, it's not like
I'm not part of it. But I'm actually part of it.
I don't understand.
Hey guys, let's talk about Mr. Mac behind his back so that way we can just get it all out right here, and then when he comes back, hopefully no one will do it.
And it's not recording,
Wait,
so
it's
it's
recording
okay.
right now?
So you know we can just talk as much.
Wait, it's recording right now?
Yes, it's record. Look. It's
Oh no.
I'm sure you had no idea.
what? Oh well, I guess we can't do that anymore. Here he comes. He has a bowling ball. Look at this. He has a bowling ball.
In the snow.
So I'm kind of making some assumptions here. We're assuming that this is effectively a solid sphere as well. But again, the idea is there's clearly more massive, more radius. You would think then that this should have significantly lower acceleration. But if you think about, because they have different weights on them, they actually have different torques on them, right? And so more moment of inertia, like as an actual value, but that ends up dividing out if you look at the way the torque is. Actually, Grant can help me out with this. Not catching, actually, it's releasing. Because I can't lift the table. Actually, no, I think I remember teacher ways. Alright, ready? It's pretty much about the same. It's pretty much the same. Yeah. So let's take a look at mathematically how to demonstrate that the mass and the radius doesn't actually matter. Okay. So, I do want to point out a couple things. Looking at the book. So if you go back, okay, let me pull this up. Nope, that's not it. There you go. Okay, if you're looking at the book, in terms of what we're covering so far, this stuff you should already know. This stuff you should already know. We just talked about center of mass. That's all of this. This is the calculus side of it. That's when you start adding up infinitesimally small amounts of stuff. This is a pretty good example to look at. See what they're doing in terms of converting dm to dx or dx to dm. Okay, we didn't quite talk about rotational energy yet, but this is all you really need to know. This is the derivation of it. All you need to know is this one. Rotational is equal to 1/2 I omega squared. Okay, and we just talked about how to calculate I. Whoops, that's this part. This part. This is calculating I. This is like the calculus version of it. I know it says delta M. It's pretty much the same idea as just the M, right? The mass of your little piece. We'll do a little more with moment of inertia next time. Hold up. 12.5 is torque. We already did torque. Okay, we already did torque. How to calculate torque? The thing we have to add on to torque is now we start talking about rotational dynamics. We start looking at this part. This is like Newton's law for rotation. Either alpha equals tau over I, or whatever, tau equals I alpha, same thing. And then the rest of it is just a bunch of specific problems. So we actually don't have too much to do now since we've already talked about torque a lot. But, well, we'll continue on next time.